Okay, so thank you to be here. I am Damien Dosimont. I'm also co-chair of this session, and I represent how we adapt the development of a CI/CD application following the CI/CD lifecycle on a DevOps approach. So the CFD application in question is ALIA, an application we developed at BSc in the case department. So ALIA is a multi-physics, multi-scale, multi-domain simulation code which simulate different kinds of physics, incompressible, compressible flows, nonlinear solid mechanics, chemistry, particle transport, etc. So a particularity of ALIA is it has been designed from scratch to run on supercomputer with parallel architecture. So it uses MPI for external communication and OpenMP. It takes advantage of vectorization of CPU and GPU using OpenSCC and CUDA. So some figures about ALIA. ALIA is quite an old code of 19-year-old. It's composed of 300,000 code lines written in Fortran 2008, and it has seen more than 100 contributors and has an history of 24,000 commits. So quite an old code and with a huge history. So the purpose of CI/CD is to ensure a certain number of things when we perform changes in the code. At the beginning, we want to ensure good specifications, documentation, and collaboration between the different developers of the code, and ensure compilation on the target platforms. We want to prevent regression. We want to ensure accuracy and reliability of the simulations, to cover the new contributions, to deploy the code on all the target platforms, and monitor the behavior to ensure that there is no problem when we release a new version. So in order to do that, we follow a CI/CD lifecycle, which is composed of two parts, CI and CD. It's quite classical. And CI has a different step: plan, code, build, and test. On CD, release, deploy, operate, and monitor. So we use GitLab to implement this CI/CD lifecycle because it proposes a Git repository to host the code, CI/CD features like pipelines and runners, and a graphical interface to manage the settings and the collaboration between the developers. So let's start by explaining how we do our lifecycle. So we start with the plan and code phases. So to plan, we use features of the GitLab, the issues, that are basically like tickets. So when we want to report a bug, we want to describe a new feature, a new enhancement of the code, we create this ticket, this issue. We describe the different modification we want to do in the code, and we can start a discussion thread to discuss between the different developers. Once everybody agree, we go to the next phase, the coding phase. When we create a merge request, this will automatically create a Git branch, which enable to work on a context that is separate from the main branch of the repository. So when we work on the branch, we perform commits. Each time we make a commit and we push a commit, we will trigger a continuous integration pipeline. So this pipeline is a sequence of steps. Each step is comprise jobs, and a job is responsible of testing a certain task. So we have different color for different kind of checks. So for instance, in gray, we have basic code checkings. In blue, we have a build on Unity and smoke test on Docker environments. In red, we have the same thing on staging environment, and in yellow, we retrieve information about the code coverage to know if it has decreased or increased. So Docker environments are useful in order to test the building and the testing of the code on a light platform without having to go directly on the HPC platform. So it's running on the top of a GitLab runner. So we always have the same OS environment, but we use different flavors. For instance, using NVIDIA compilers, WinAPI compilers, new compilers, etc. And we basically compile ALIA using CMake. So the choice of CMake has been done because it enables to compile on different architecture, on different with different options easily. So we generate the binary, and we use ctests that come along with CMake to run different kind of tests. So we have unity tests that serve to test a particular feature. So each time we add a new feature, a new functionality in the code, we add a corresponding test in Alia. And we have smoke tests that are whole execution of Alia, but without testing the output. We just want to ensure that we don't have any crash, any segmentation fault. So then we have the staging environment test. So we have a tool that is responsible of this part. So it's triggered from the GitLab runner of Alia, which triggers the Squidient pipeline. So Squidient is the name of the tool. And it does basically the same thing as for Dockers. We run CMake, we generate the binary, we run ctest. We also have regression tests that are more complex tests. We get information about the code coverage from the test, and we run all of this on the HPC platforms. So the interest of Squidient is it is able to manage easily the different HPC platforms we want to connect to. So we use for this JSON configuration file like on the left, where we describe the HPC platform we want to connect. So we describe the architecture, the text per node, the CPU per task, etc. We describe the installation path of the different tools we install to make the Squidient work, and the queue we will use to run the different jobs. And we connect using SSH, and we need Slurm on the platform to make the thing work. So we generate different kind of jobs, jobs for building on running the Unity and Smoke test, and jobs for running the regression test. So the regression tests are basically small simulations that are composed of input data, geometry, kernel, and physics module configuration, JSON configurations that explain basically how we run the simulation, and output reference value files. So the idea is to compare the results with reference value using tolerance methods to take into account the precision error due to the compiler, the architecture, the compilation options. So we aggregate multiple executions within a single job to prevent Squidient from overloading the Slurm queue. And we also have a fault tolerance mechanism that will launch the tests that have failed because of the HPC platform issue. So we are basically driven by the code coverage, which means that when we run Squidient, we get information about the code coverage, the global code coverage, if it has decreased or increased. And if it has decreased, we have information about which lines are uncovered. So we'll ask the developer to cover these new lines, the line he has added to the contribution, by creating new tests, smoke test, unity test, or regression test, in order to satisfy this need. So some results about build and test. So for the Docker environments, we have 16 builds for GNU, one for one API and one for NVIDIA. For the staging environments, we have 16 builds for -5, 7 builds for AMD cluster, and 1 build for an accelerated cluster. And we have more than 100 unity tests and 600 regression tests. About the timing, so it's important because the idea is to run the pipeline in the less time possible in order to run the most merge requests possible. So we run a pipeline in more or less 260 minutes, which enables to reintegrate 2 or 3 merge requests for a working day of 12 hours. So about the CI, so between 2020 and 2024, we closed 2,000 issues. We have still more than 100 active. We reintegrated 1,300 merge requests, which means more or less 1 merge request a day. And we have, in average, 30 merge requests active a day, 30 merge requests active. We have an history of 20,000 commits, and an average of 9 commits a day in the master branch. And the code coverage has increased of 40% between 2020 and 2024. So now let's speak about the continuous deployment and more specifically on the monitoring the performance. So we still use Qdiant to perform this task. So following the same principle, we use CMA to compile, we generate the binary. And what is interesting is Alia is instrumented by default to generate metrics like the time passed in some part of the code, the memory usage. We also are connected with an external library, which is called TALP, which provide information like the load balancing, the communication efficiency, or this kind of things. And we run benchmarks that are like simulations running on several nodes and HPC platforms. We store the results of the metrics on a database, and we visualize this information on a tool we have developed, Rooster. So here we have a different visualization. On the top, we have an overview that show at which point that show the global behavior of the benchmarks. So when we have spikes, it means that one of the benchmark lasts longer than normally. So on the left, well, it doesn't work. On the left, we have a first spike. So when we click on this spike, we get more information on the second graph that is connected. And we see that the green benchmark lasts much longer than normally. And when we click again on the second graph on this benchmark at this point, we get more information on the third graph. This graph gives information about the proportion passed in the I/O, the communication, the computation. And we can see here that we have a huge increase of the I/O operation. So speaking with the support of Mare Nostrum, we get information about some incidents on the platform. So this is interesting to have information about what happened on Mare Nostrum. So we can find this kind of problems. It's also useful to detect some bad programming. For instance, when we degrade the performance due to a bug in the code or this kind of thing. So this is something we find regularly in the code. So let's speak about the future works. So we'd like to integrate in our pipeline static code analysis like proposed by Cody. So in order to reduce our technological debt, we also want to put tests in our pipeline that integrate GPUs. For the moment, we don't have anything like that. We would like to deploy and to test the building and testing on Euro HPC machines. For the moment, we are just running our pipeline on the BSC platforms. And we also are integrating more information on our visualization. For instance, here we show the different incidents. So the dots on the graph show the different kind of incidents that can occur on Mare Nostrum. We also want to add new information like counters, hardware counters, or temperatures, this kind of things to help the user to relate the performance issue to the machine behavior. So thank you for your attention, and let's move on to the questions.